Hi, I'm Walter Grayman, representing the Environmental and Water Resources Institute, EWRI's WDSA History Project. The purpose of this project is to document the history of water distribution system analysis. An important part of this project is a series of interviews with engineers, modelers, researchers, and practitioners who have made significant contributions to the field of water distribution system analysis. Our interview today is with Dr. James Huber. Jim is a professor in the School of Energy, Environmental, Biological, and Medical Engineering at the University of Cincinnati and CEO and founder of City Logics, LLC. He has over 25 years of research experience in water infrastructure systems modeling, optimization, and control. In the late 1990s, Jim initiated the WDSA Symposium at ASCE EWRI conferences, an event that continues today on an annual basis and serves as the primary international outlet for the theoretical developments and applications of systems analysis to water distribution systems. This interview is being conducted on March 25th, 2015 in Covington, Kentucky. Jim, as the founding father of the ASCE EWRI WDSA Symposium Series, and subsequently this WDSA Committee, can you provide some insights on how this came about and its role over the past 15 years?
Well, back in, I would say the mid-1990s, there was always been a lot of people doing work in water distribution systems analysis, and yet at these, at the Water Resources Planning and Management conferences, which is what they were called then in the ASCE, there wasn't any sort of coherent set of sessions where everybody would come together, so things would be scattered throughout. So one year we just tried to organize, I think, a modest number of sessions, 2 or 3, invited some people that were, well known in the field, and wanted to see if they would come. And it was organized, as I recall, around water quality issues, I think, because that was still a bit new at the time. And it turned out, I thought they were just really successful. It wasn't hard to do. And so the next year, as you'll recall, Walter, which is when you were leading up the conference in Tempe. So I don't think that we would have really started this at this scale unless you were doing that, and unless you had asked and said, I think if you want, we could make a go of this as a track at the conference. And I was a little bit hesitant to go from a couple sessions to a track, but with your encouragement, gladly decided to do that and help organize it. And I think we turned out enough abstracts for almost an entire track, if not an entire track, and after then it just became sort of a natural thing to do, and after a while the ASCE and EWRI came to expect us to do it, and different people have gotten back and forth in terms of heading it up and organizing the sessions, and it sort of runs on autopilot now, and it's been a great success.
How and when did you first become involved in research related to water distribution system analysis?
Well, I didn't know anything about this area when I started as an assistant professor at University of Cincinnati in 1990. We had the good fortune, and still have the good fortune, of being close to the US EPA Research Lab, and I had the great good fortune to get to know Louis Rossman, or Lou as we know him. And at that time, he also was just getting started in his work on water quality and water distribution systems and modeling, building off of the work that you and Dick Mayles had originally done with Bob Clark. And so one way or another, I can't remember exactly how, the US EPA got a project together to look at how to operate water distribution systems for water quality issues. This was back in 1991, and I became associated with that project from the UC side, and Lou was the project manager. And we worked together on this, and in retrospect, honestly, it was just a project that, in terms of what I contributed, was way ahead of its time. I mean, we didn't have either the knowledge or the computer power or things to do the kinds of things that we wanted to do, certainly for real water distribution systems. We were trying to figure out how to turn pumps on and off in order to reduce residence times and storage and things like that. It was pretty challenging. But as a byproduct of that, I just learned a lot of things that I needed to learn about the models, the hydraulics, the water quality, and associated with that project, I think honestly, because we were developing some of the codes that we were producing for the research project in Fortran, and Lou thought that we were probably just hopelessly, I should say, antiquated. So he went off and developed QHCPAC, which was the precursor to EPANet, and that was around 1991. And I remember sort of during the middle of that project, Lou presenting us with QHCPAC and saying, "I think you guys should seriously consider using this instead of what you're doing." And after that, we just had the good fortune of continuing to work with Lou as he continued to develop EPANet and develop the API, the toolkit that allowed researchers to use EPANet for research projects, and it was a really fun collaboration from my perspective.
Much of your research efforts in the WDSA area have involved researchers from outside of the traditional civil engineering field, including epidemiologists, public health, electrical, and chemical engineering. Have you found such collaboration to be useful? Have you found difficulties in working with researchers that may speak a different technical language?
Yeah, that's a great question. The collaborations that I've had with some controls-oriented people that were, in my case, more on the electrical engineering side. Marios Policarpou was a great colleague now at University of Cyprus, was at the University of Cincinnati, had really fun collaborations with him. Those and others, those were really relatively easy, interesting. I remember that Marios and his team always wanted to look at, the controls folks have an idea of, it's a box that has an input and it has an output. And so they would always talk about, well, what's the input-output model of this system? Because, once you, as a controls person, if you understood how the input-output behavior, was governed and you could describe it in some way, then you could do interesting control things. And that was just interesting. They would look at all sorts of things a little bit differently. A least squares, optimization problem for model calibration in their world was recursive least squares, and it operated in real time, in continuously ingesting data, which I'd never heard of, and yet at the same time, when you studied it, it was kind of the same thing. And I remember he also had a student, Mike Zeroff. And Mike Zeroff was the guy. He came to my office, and he was a person who really first developed this idea of backtracking from sort of an output back to an input, and developing this backtrack model, which we used afterwards in a few studies and still do. And I remember him coming to my office and saying, I really wanted to figure out this input-output model, and I said, I think that would be great, but I don't understand how you do that for something like a distribution system. And he, went out and studied it and thought about it in a different way, and he did it. And I doubt if he's, I don't know, but he probably hasn't worked in water distribution systems since, but he made, from my perspective, a really nice contribution. Epidemiology was different for me. It was, again, fun and interesting, but it was much more of a process where you had some knowledge that they didn't have, and they had some knowledge that you didn't have, and you were trying to blend them together. And there were always questions, understandable ones, about, how you were doing, what you were doing, and what did it mean, and what were the limits of its accuracy, and so sometimes those meetings and those the progress was slow as a result of that. But probably necessarily slow. And I think that honestly, there's been several huge studies that are expensive, that are epidemiology focused, that try to figure out things like, are we being harmed in some way by the water that we drink? And the norm appears to be that those studies are done by people that don't know anything about the actual physical systems, like the transport and the infrastructure and how they're operated. And almost sometimes it seems like there was a bias that I shouldn't know too much, because if I knew too much, it would cause me to design my studies in a way that would not be sort of statistically sound anymore. In other words, I'd be doing what an engineer does, which is to say, I think that this is the cause. Let me go out and prove that it is the cause, or prove that it isn't the cause. And they want to not have those questions even in the room. And that was very interesting for me and frankly frustrating. But fortunately, the folks that I worked with from an epidemiology perspective saw the value in having the engineering blended with the epidemiology in some way, and thought that the project was better as a result.
In the 1990s and I think into the early 2000s, you had several research projects related to the optimal design and placement of booster chlorination stations. Can you provide some insights on how you became involved in that area of research and some thoughts on the outcome of that research?
Sure. Well, that was those were not my idea. That was the idea of somebody that I don't know who it was. It was an AWRF project. The first one was, and I had another one that was also an AWRF project. I think that at that time there were increasing concerns about just maintaining a chlorine residual. Booster chlorination was being done at that time, but there was a lot of things that were unknown about where to locate them and what benefits it had and things like that. So I think that was the intent of that project. How I really got into that, however, that was the first sort of real water distribution project I had that dealt with real utilities after the initial one with Lou Rossman. And I decided to really, that was a time when I really decided to invest in this area. And I remember it was sort of because my background was kind of applied optimization and systems analysis, a little bit more generally. I'd worked on wastewater treatment plant optimization problems for design purposes and uncertainty analysis in the past, and people frankly weren't doing optimal design of wastewater treatment systems. And then I was working a little bit on groundwater, and there was a lot of literature, and still is, I think, in the groundwater area about optimizing groundwater remediation systems. But I worked on that a little bit and became frustrated with the just the tremendous uncertainty of the subsurface environment. And I wanted just frankly, I'm fairly practical, might surprise some people, but I've been told that. I wanted to work on something where I thought that the basis of what I was doing, which was the predictive model, had a chance of being correct. And I thought, well, I think these water distribution systems are pretty interesting, and I know a little bit about them now. And in principle, at least, you can understand it because you built it. And that was different from the groundwater and the subsurface environment, which is natural. And so I think that really drew me to investing more heavily in this area. That's what made me write a proposal for that AWRF project. And thankfully we were successful in winning that. Now, we had a lot of fun with those couple of projects. Honestly, I don't know if anybody has ever used our techniques for optimally locating booster disinfection stations. They all seem to be located at storage tanks. I suppose there is an optimization problem about which storage tanks to put them at. We spent a lot of time sort of understanding the system, and there were some other good things that came out of that. The input-output model and things that I referred to earlier, was part of that, and some concepts in control of water quality, came out of that. But I think that it was a project that, like some research projects, serve to teach you about things that lead you to other things which maybe have more practical value. And I don't expect I'll be writing any software for optimally locating booster stations in the future. So.
Following the events of September 11th, 2001, there was a concern in the water industry about potential contamination, terrorist contamination of water distribution systems. And US EPA started their National Homeland Security Research Center. And in the 2002-2003 timeframe, you worked with them, I think, probably close to a full-time basis, aimed at mitigating the risks associated with intentional contamination. What do you consider to be the most important contributions from that collaboration?
Yeah, that was, I worked with them full-time for almost 2 years. I took a leave of absence from UC for part of that time, and also UC granted me a sabbatical to work with them. And it was very important for my career in a number of ways. The most important contribution, I remember writing an email to Tim Oppelt. Tim Oppelt was the director of the new, at that time, National Homeland Security Research Center. And I said, I heard about this research center that you guys are doing. I think that I have some skills that could be helpful that you might not have. Because, for example, Lou Rossman was not part of that effort. He chose to stay in his laboratory at EPA instead of joining that. And Tim replied to me, great, let's get together and talk. And I remember at that initial discussion, we were talking about how vulnerable a distribution system is, and is it vulnerable? And at that time, there was a lot of uncertainty. There's too much dilution. Nothing could ever be introduced into a distribution system with sufficient quantities where it could harm anybody, or it would never make it into somebody's actual tap water. And so we decided to sort of tackle this problem of let's use our skills, which were modeling based. We knew about water quality modeling. We did some fairly simple and frankly pretty standard hydraulic and water quality modeling to start to look at what the risks were. And this took us, of course in a terrorism, as frightening as that would be, in that kind of a scenario, one of the things you had to confront was that you would never know where this would happen. And in principle, because of service connections to the distribution systems, it could in principle happen almost anywhere. So this led us to this very simple idea of just doing a bunch of simulations, calculating where the spread of contaminant would go, locating the possible sources at many different places, essentially just looking at an ensemble of different simulations and aggregating them together statistically to calculate what the likelihood would be of an adverse health outcome. And as soon as we did that, even in a very preliminary way, I remember, and this was with Rob Janke and Regan Murray, we all did this together, and that was just great, exciting times, working late into the evening on these things. We showed some preliminary, very rough sketches to Tim Oppelt, and he was just immediately saw the value in that. It spoke to him, and he said, this is what we've wanted. We needed to know something about what even the order of magnitude impacts were. And I'll tell you, Walter, I was and still am today very surprised about the way that unfolded and the impact that some fairly modest results put together with some standard industry tools and a little bit of programming had. I mean, it generated visits from people from Washington at reasonably high levels. It, in one way or another, with a lot of other people's shepherding and a lot of help, in one way or another led to the the program of instrumenting 5 or 6 utilities in the United States with expensive sensor systems for mitigating these impacts. It led to the TIVA research program, which has software associated with it, but of figuring out how to do this vulnerability analysis. So I'd have to say that had the most impact. I can't, in all honesty, say that I support all of the things that happened as a result of that, but it certainly had a sizable impact on putting sensors out in water distribution systems and a whole lot of other things that I could have never anticipated.
Your group at the university, in collaboration with US EPA, developed the EPA-NET Multi-Species Extension, MSX, that integrates multi-species water quality and dynamics with water distribution system hydraulic models. What motivated that research? Are you satisfied with the level of acceptance of the software by the water distribution system modeling community?
Yeah, so I had the pleasure of working with Feng Shang, who was a PhD student of mine, but he was a postdoc at the US EPA, and he wrote that first version of MSX and did that sort of core research. He was advised in doing that by me and by Lou Rossman. Lou then took those results and incorporated that into a sort of fully fledged computer program that met all the quality standards that the EPA would require of it. And that was, I still think that's the way that water quality analyses need to be done. I won't say that I'm satisfied, but I'm certainly not surprised by the I would say slow absorption of looking at more than one species into practice. I do hear of and am sometimes associated with water utilities even, and people in the consulting community that are aware of and are working on developing multi-species models. I think appropriately, sometimes they're relatively simple ones, like I've got a source blending problem, and I want to model that a little bit more accurately or a little bit more seamlessly than I can with ordinary EPA-NET, or I just want to model chlorine residuals with a little bit more accuracy than I think I could otherwise, and this allows me to have more control over the water quality kinetic expressions. I think that is definitely desirable. I think probably eventually we'll have more complexity in the water quality predictions that we do, but only after we sort of decide on what the stylized problems are that we need to solve and what the appropriate models are that we need to solve them, and they're built into end user software. I don't ever expect anybody but researchers to do something like you're doing with MSX, whereas you specify the water quality reaction kinetic expressions and the species and all that kind of thing. For that, frankly, one of the things that holds us back is that a large fraction of the people doing distribution system modeling have never had a course on water chemistry. I have the benefit of having an environmental engineering background, as opposed to a water. If I had gone across the street at University of Illinois and been in the water resources program, I probably wouldn't know what chemical reaction kinetics was, possibly. That's an overstatement, okay? But in contrast, the folks that are really into water quality, and water chemistry don't know much about water distribution systems and hydraulics and modeling. So I hope that eventually we get to these ideas where we have, okay, this is the best way to model chlorine and their interactions with natural organic matter. This is the best way to model disinfection byproducts and whatnot. And those will probably be multi-species models, and we'll figure out how to estimate their parameters from field data. And we just really frankly haven't done that yet.
Thanks. For the past several years, you've been deeply involved in research and development in the area of real-time distribution system modeling, driven by integration with operational data. Though this area has been discussed within the modeling community for probably the past 30 years. It is only within the last few years that it has achieved some level of traction within the industry. Can you describe your thoughts on this subject and what you see happening in this area in the next decade?
Oh, sure. This is really near and dear to my heart. It's something I spend, most of the day on, these days in 2015. I just have the good fortune of, I think, having come at this problem of whether you call it data assimilation or data fusion or real-time modeling, whatever it is, they're sort of in some ways the same thing. I just have the good fortune of coming at this, I think, at the right time. I was ignorant about it almost completely until 2004 or 2005. I remember David Hartman, who worked for Greater Cincinnati Waterworks, came to the U.S. EPA when I was working with them at the Homeland Security Center, Research Center there. And he was saying, well, all this vulnerability analysis work that you're doing with Rob Janke and Regan Murgy, this is great, but David had a very practical way and a very kind way of saying things, but I think what he was really saying is that, it's all based on models that we're using for planning purposes, and do you really believe what you are doing? Wouldn't it be really much more useful if we first started to talk about taking all this SCADA data and linking it with the models? And of course, that wasn't a new idea in 2004 either. Like you said, it had been discussed well before then, but it got the seed working in our, growing in our minds about whether this is possible to do. And that seed slowly grew into a dissatisfaction with the way that we were doing, at least some of us, it was a dissatisfaction with the way that we were doing the vulnerability analyses, the sort of static assumptions that were being made. And do we need to really be doing these water quality simulations about, more related to an ensemble about how this utility has actually behaved over the past 5 years or 10 years, or instead of based on assumptions that were used for master planning, largely speaking. So we started to develop, some of the infrastructure to allow us to do that. And I guess that's evolved. I have had the great good fortune of working with who is now my colleague, Sam Hatchett. And I remember him, we developed a first version of this software called EPNet RTX, which is an open source software program that provides the linkages between data and the hydraulic and water quality modeling and allows that to be done in programming, at least relatively simply. And we developed a first version of that, which was very primitive. I mean, it didn't even have a notion of a database in it. And he came in and he kind of sat down, and he was a student at that time. He said, I really think that there are these things called databases that we should be taking advantage of if we're really serious about doing this sort of on an industry scale. And as you can tell, I was really pretty naive about this, a lot of these types of things. And so from there, started to developing more of the, what I would sort of call industrial scale software, which embeds all of this time-consuming, difficult things to do about connecting via ODBC connectors to industry standard database formats, and things that for any student, for example, doing a research project would take them half of the time just to figure out how to do once. It was necessary to have that infrastructure for data access. And then we needed to have the ability to, deal with what, Tom Walski always admonishes us about is SCADA data really isn't all that useful. And so how do you actually use it usefully with a model? This is true. Tom Walski has never said anything with that amount of conviction or anything else for that matter that really isn't fundamentally true. So we had to have that. Now that you could access the data simply, you had to have the ability to transform it. And it had to be easy. It can't be, I have to, code up a 5-point moving average filter every single time I need to do something. So we had to have, the filters and the data smoothing algorithms and the ability to deal with data gaps. And to do all that, simply. And so that was the sort of transformation layer. And then after that comes synthesis. And I'm actually through this building up to where I think this is going. But you have to have these pillars. You have to have the ability to easily access data. You have to be able to transform it in useful ways. Then you have to be able to synthesize something from it, because there's a lot of talk nowadays about smart water infrastructure, and it all seems to boil down to more sensors with more data, more cheaply in more places. But that doesn't generally necessarily yield anything that is smart. In fact, it can make you dumber if you don't do it wisely, because you just get inundated. So synthesis means taking something from those data and produce something new of value out of it. And those of us in the hydraulic and water quality modeling communities know one of the biggest ways we synthesize new information, is from models. So you take the model, the data that you've accessed, that's real-time operational data, you transform it in ways that are necessary for making it useful. You figure out a way to easily hook that into a model so that a runtime meter on a pump now becomes a 0-1 status that's driving that pump on and off exactly when it is actually being on and off in practice or in real life. And then you have the ability to synthesize, using our existing models, information that for some purposes is of higher value than our normal simulations have been for master planning. And I think that water quality simulations are often that way, because I don't think, unlike hydraulics, I don't think we have the master planning sort of scenario for the water quality analysis. We don't have the max day with 3 fires situation that allows us to say we do water quality analyses under this scenario and we have something meaningful. So I think, broadly speaking, in my view, for making all of the work that the community has been doing for water quality simulations of value, I think, in my opinion, we have to do that by data-fused, realistic water quality simulations, because the results, I just think, are too sensitive to the way the systems are operated to do anything else. So I'm very curious. The last word is far from being written on that, but I'm very curious to see how the value of water quality predictions is perceived when we're actually ultimately doing them, and I think we're very close to doing that on a routine basis, for the way the systems are operated really truly in real life. And I'm frankly very eager to see whether or not the hydraulic and water quality models go from being maybe trusted by the engineer for the hydraulic models, but probably not trusted by the engineer for the water quality models, to maybe even having both of them being trusted by the operator. I think that's the holy grail that I've painted.
Any other thoughts that you would like to share with us about your work in water distribution system analysis and maybe some of the directions for the future?
Oh, I think I've probably taken up more than my allotted time at this point. I'm humbled to be part of this effort. In retrospect, it's been great to work with all those folks that I've mentioned and others, certainly. I think it's a very exciting field. I think that I'm always frankly astonished that more people don't flock to this, because if you're interested in anything from programming and software development to numerical methods to just practical modeling of some of the most complex systems that man has devised that are critical to our daily life in cities, and so critical and so well designed that we frankly don't think about them. Then they're fascinating to see how they behave. And going back to an earlier comment that I made, I think that one of just the coolest things about them remains that, in principle, we built these things, and although we may have forgotten some of the decisions we made, when we built them, in principle, we can figure this out. And it really is a matter of the value that we will ultimately ascribe in figuring out how they behave. And that is totally linked to the accuracy of what we can provide. And, I'm telling you, there's a whole bunch of people out there that if you said something as simple as, I can carve up your system into, different demand zones, and I can predict within 3 psi the minimum pressure in that zone as a function of your operating policies. There's tons of people that will never believe that you can do that, but there's also equally, probably more people that if you could convince them that you could, they would be interested, and they would think that that would have a lot of value to a lot of different people in the utility organization. And the ability to even conceive of doing something like that with one of these really complex engineered infrastructure systems. I saw a model recently, 300,000 elements, hundreds and hundreds of discrete devices going on and off all the time. This is fascinating stuff. So I would encourage anybody who has an inkling and doing work and modeling and anywhere from practical to the research side, you want like an interesting, fascinating model calibration problem. This is one place where you should be looking. So,
Jim, thank you very much for your time and your insights.
Absolutely, Walter.